So thanks for coming. As I said yesterday, I decided to devote this hour, instead of just continuing with the tutorial, I took the opportunity of the fact that well-known experts in information theory are in the crowd, and therefore the purpose of this informal session is to present several open problems, long-standing open problems in theoretical computer science, which are purely information theoretic. So there is no computational aspect to these questions whatsoever. Nevertheless, answering these questions will have far-reaching consequences on lower bounds for computational models for circuit lower bounds, for data structure lower bounds, and even for algorithms for solving SAT formulas, for example. And the common denominator of the three problems I'll discuss, it's hard to state this precisely, but in some sense, you'll see that the common denominator is that all of these problems will share the common denominator that we have a very poor understanding of how do we quantify complicated correlations between random variables, which simultaneously need to satisfy certain marginal or conditional independence constraints, but somehow they can create very weird correlations as a joint distribution. It will probably be reminiscent of Andre's talk from Tuesday. Really, all three problems which I'll present we essentially don't know anything. So the gap is essentially as large as it could be, and we're really desperate for new techniques. So that's the theme of the talk. The first problem we'll discuss is secret sharing. By the way, so this is an informal kind of discussion type session. Feel free to interrupt. And there is no, I mean, if we don't make it to the third problem, that's fine. It's depending on the interest. And So the second problem is the set disjointness problem in the multiterminal or multi-party number on forehead model. I'll assume no prior knowledge, so I'll define everything throughout the talk. And the third problem is a problem which is probably most of the information theory people here are well familiar with, is the problem of index coding, which has applications in both in theoretical computer science to proving superlinear circuit lower bounds, and it's interesting on its own right. So this is the plan for the talk. I'll hopefully spend 10, 15 minutes on each problem, and depending how it goes, we'll proceed. So how many people have heard of secret sharing? Okay, so maybe we can move faster because I don't have a lot of interesting result to state. So basically, what is the secret sharing problem? A sender or a central authority, let's call it Alice, she has some secret information, which for simplicity is just a uniform bit, or k uniform bits. And she wants to share this secret with, I want to share this secret with n players, with all of you guys. But I want only certain legal subsets of the players to be able to discover this set. So this is formalized by the notion of an access structure. An access structure is a function that receives, that defines basically the set of the subsets of legal. It's the family of subsets of legal participants which are allowed to discover the secret. And the requirement is that if a subset of players is legal, so it's inside the access structure, then we require that it learns the entire secret by joining the. Okay, sorry, I forgot to say. So how will I distribute the secret? I will compute some function, which is a randomized function. So I will compute a function which is a function of the true secret and some private randomness. I will distribute k bits per player in the crowd. And I require that if T is a subset of legal, is a legal subset of players, if it's inside the access structure, then I require that by combining the shares of the people inside the subset T, they can infer the secret, so they just learn the entire secret. And otherwise, I require that they learn nothing. So I require that the mutual information between the secret and the concatenation of the shares of an illegal subset is 0.
Is there a minimum size
for T? For T, the subset of players? No, that's, I mean, that's, the only requirement on T is obviously, this is a natural property, is that it's a monotone set, it's a monotone family, right? If a superset of a legal family of functions is convenes, obviously they should be able to discover the secret. Great question. I don't know. I don't think, I think people have looked at this. I don't know of any result that applies to this weaker notion, but does not apply to, in fact, we'll see that the state of the art in this field is so weak that we, even for the, yeah, at least in terms of lower bounds, yeah. But the easy cases, we can deal with the stronger requirement.
I think one can imagine situations in which you don't want to
in which you don't. That's.
But it's up to you. What do you mean? How can we avoid monotonicity? Is a group that knows something that just variables are known?
Yeah, but so that it will be, but suppose if more of them a larger goes, there may be some kind of catastrophic.
Yeah, well, if they're allowed, yeah, if they're allowed to just concatenate their shares, then, yeah. Okay, so is the problem clear though? So there are no computational aspects. It's a purely information-theoretic problem. And the first thing, okay, so what is the interesting parameter here? What is the most natural question? Well, the question is how many shares, how large of a message do I need to distribute each one of you guys in order for this constraint to be satisfied for a given access structure, right? So I pick my favorite subsets of a family of subsets of legal players that I want them to be able to infer the secret. And the question is what is the share size? What is the information ratio of this scheme? Which is basically the ratio between the number of the share size I distribute to a player and the secret. In our case, mostly we'll talk about 1-bit secret. So it's just the maximum per player share. Does it make sense? Okay, so first of all, notice that it's not a priori clear that we can even implement with any with a finite number with finite share sizes arbitrary access structures, right? It's not entirely clear, but it turns out that indeed, if you allow me share sizes of exponential size in the number of players. And I remind you, just to distribute just 1 bit of secret, we're going to spend exponentially many bits per player. Sounds very embarrassing. Then we can do that. We can implement any access structure. And
Maybe just need one for every leaf of it, because you can just do an XOR, which just like for those particular 2 would be the worst case, but for every, if you give me an access structure, then you can just create an XOR on those things. But everything is independent, so you can create XOR for each access set.
so let me just sketch the proof. So as we said, an access structure, let's call it A, it has to be a monotone function, so it's completely defined, it's characterized by its min terms, the minimum subsets of players that can infer the secret. So suppose I have this term, the first player and the 17th player and the player number 20. So this is a min term. Yeah, sure. So suppose I have, so what is I can represent this access structure by the concatenation, by the disjunction of all the minterms. What is a minterm? It's just a minimal subset of players that can infer the secret. So suppose it's the first player and the 17th player and player number 21. Then what can I do? So I will use fresh random bits to encode each minterm. So what I'll do, I'll give the first player the true secret, XORed with some random bit R. I'll give the second player this bit R XORed with some random bit R prime. I'll give the third player this random R bit R prime. So these are just independent, R and R prime are just independent random bits. And you can see that if they just convene together, they can just XOR everything, and this sum just telescopes, right? So everything will cancel, and they will recover S. Okay, so, and we can repeat this scheme for every minterm with fresh randomness, and this will work, and this will yield exponential size shares. Okay, so at least we have some finite upper bound. Let me give you an example of a special case in which we can do much better than exponential size. This is maybe the result that in some sense initiated the field. This is a classical secret sharing scheme of Shamir, which treats a special case of access structures of threshold access structures. So a natural access structure defines the legal subsets to be, I require that any subset of at least 17 players will be able to decode the secret, right? So it turns out that such access structures you can implement using much better, in fact, optimal ratio. You can distribute, in this case, it will be more natural to look at not 1-bit secrets, but log n bit secrets. And you can do this with a log n share size per player, which is optimal, which is kind of, you're encrypting log n bits of information using log bits of shares. And I won't do the entire thing. The scheme is based on this very nice idea of polynomial interpolation. So what I'll do is the following thing. I will choose a field size Q, where Q is, is at least the number of players, okay? And remember, what I'll do is I'll show you how to distribute a secret of size log Q. So basically an element of the field. Okay, this will be the secret. It's a generic log qubit message. And what I'll do is the following. I'll set this secret to be the first element, basically the free variable of a polynomial. This will be the secret. And then what I'll do is I'll choose basically a random degree t. The threshold, remember, is t. So it's an arbitrary number between 0 and n. And then I'll choose just a random degree t polynomial, degree t or t minus 1, I forget, polynomial. And basically what I'll do is I'll give the first player a1 x. Just a second. So the polynomial will be so basically I'll choose random coefficient. So this will be just a random polynomial whose free element is the secret. So basically it will be just a random polynomial. And what is the share that I'll distribute each player? I'll just give him the evaluation of this random polynomial on, an arbitrary element of the field. Okay, and then it just, so the completeness is pretty clear, right? If you have t points of a degree, t evaluations of a degree t polynomial, you can exactly decode the polynomial. Therefore, you can reveal the free element here. The less trivial part is that if you have a degree, any t minus 1 players, even if they have the evaluation of t minus 1 points, the remaining, basically the polynomial, to understand, basically the polynomial will be random in the sense that the free variable will be completely random. It's not a completely trivial fact, but kind of intuitive. Okay, so this is a very nice scheme, and it shows that, at least in some natural, it really shows that the structure, right, of the axis structure really matters. It's very important. However, but still, what happens for general axis structures, right? We saw an upper bound of 2 to the n, right, exponential, which is very, which is very unfortunate, right? We spent exponentially many bits to distribute just one bit of secret. And while in fact it's widely believed that this is optimal, that there are axis structures, and I'll give an example, the natural candidate, I'll give it in a second. It's widely believed that there's an axis structure, there are axis structures that do require exponentially many bits just for 1 bit secret. However, the best lower bound we have for this is not even linear, right? So I think this is the problem with the largest gap I know, probably. So it's the bounds, and even for this, people had to work really hard. So it took like, how long? I mean, it took some time to prove that. And I won't elaborate on the proof, but the way the proof, so this is the state of the art, and it was proved using those so-called Shannon inequalities that I presume that Henri talked about. What's surprising is that after this proof was given, it was discovered that, in fact, using these techniques of Shannon-type inequalities, which are basically information inequalities that basically captures some of the properties of secret sharing structures. For example, a type of such an inequality would say that if A is a legal subset, right, of players that is allowed to decode the secret, but B is not a legal subset, then the entropy that A has is at least larger than B by 1 bit, because it will recover the bit of the secret, right? So these are the type of inequalities that that appear in those.
A contains B.
Right. Sorry. Yep. Yep. Right. Yeah, good point. So, right, so after this proof was given, it was discovered that this, if you restrict yourself only to these type of inequalities, you cannot beat this bound. So if you ever want to reach even a linear lower bound of a share size per player, you must go beyond the realm of these inequalities. And I view this as a encouraging, I guess, an encouraging direction to follow Henri's non-Shannon type inequalities. And let me tell you, so really this is all I wanted to say about the problem. Basically, that's where we're stuck for like 20 years or so. I want to say just one thing, which is, this is really the most, I would say, embarrassing thing about the problem, is that, even for circuit lower bounds, we always have a counting argument. We always, to prove a lower bound on random functions or non-constructively is always easy, because we say, a circuit of type of depth d can only compute like 2 to the d functions. Here, there's no counting argument. So I claim that we cannot beat this bound even for implicit functions, even for random functions. So can anyone guess why can't we just count? Why isn't it true that a k-bit secret sharing scheme, why can't we upper bound the number of functions that it computes?
Only what we have here is like how you share what are legal in the legal sense. And you have a lot of different ways how you spread around.
So the answer is that, right, so the answer is that while I'm only distributing k-bit shares, I have an access to an infinitely many random bits. So presumably, using only k-bit shares, using a crazy number of random bits, I can create very, very weird correlations. So we cannot basically the number of distributions that can be produced using only k-bit size shares are unbounded essentially, or I don't know, they're huge. So I think this is the only example where I know that even non-constructively we don't know anything, basically. So this is how miserable the state of the art here is. So yeah, so I wanted to say one more thing, which I think is so this is really like this is the holy grail, right, to prove those lower bounds for generals. Sorry? I don't remember. It's not. It's kind of tailored to the proof. You'll see. I don't remember the access structure. It's not a. Oh yeah. So this is an explicit function, which is not. I don't remember. Yeah. So people. Oh, so let me just tell you the candidate hard access structure. It's very natural, actually. So what is? So how? So I claim that people conjecture that the following access structure, it's a randomized access structure, requires indeed, 2 to the exponentially many bit size. And what you do is just focus on the middle layer of the lattice. So it's all possible subsets of n over 2 players, and just pick half of them at random. Does it make sense? And then, of course, just, take the monotone complement, the Cohen over it. Okay, so that's a well-defined access structure. And intuitively, this access structure, if you view it as a function, it has a lot of entropy. So it has but that's, I guess, pretty much the only intuition I have. But so this is what Klimas did. It's an explicit complicated one. It's kind of tailored to the proof. I don't remember fully what it is. Okay, so yeah, so I can say some more things that will maybe strengthen the intuition for why this should take basically an encoding argument that fails. But yeah, so that's, if you're interested, I'll be happy to elaborate offline. There are other questions about specific access structures of certain types, such that for these special cases, still we don't know a lot. For example, graph type access structures for undirected graphs, the best we know is n to the log n share sizes, and for directed graphs, we can do it with 1 bit share size. So there are many interesting questions, and really, we don't have tools for this field. We're just desperate for new tools. Yeah, so let me just move on. So let me keep track for a change. Let me keep track of time. How much time do I have? 25 minutes. Okay, so how many have heard on the number on forehead model? Good crowd. Okay, so the number on forehead model is a multi-terminal, multi-party communication model, where each player has, okay, so we have k inputs, x1 through xk, which are associated with each player. But the twist is that, unlike the natural model, each player sees all the inputs except his own input. Right? So the input of player I is on his forehead, so to speak. And this is where the name comes from. So is the input distribution clear? And how does the communication, what is the model of communication? So the players have a shared blackboard, and in each round, the communication proceeds in rounds, and in each round, each player can write a message on basically a broadcast type message. And yeah, and what is the communication cost? It's just the number of bits that is, so in the first round, the second player writes some message. In the subsequent round, player number 17 can write the next message, which is a function of his own input, which is basically what he sees, and the history on the board. So he writes the second message and so forth. And the communication cost is just the length, just what's, the message length that's written on the blackboard, basically the content on the blackboard.
How do you keep track of who speaks next?
So is that, okay, so what I one way to, I guess, to solve is that in each round, all of the players can, I guess, simultaneously write, however bit. Another way is to just, I don't know, I'm not sure, Anoop, is there any?
Protocol defines, for every sequence of bits, it sets rules and makes it. Different people have different views of the input. They all use Blackboard, which determines the sequence. Blackboard plus their own views of the other people's. Not just the Blackboard, might determine
Okay. So you might ask, why is this model useful? It sounds like a very contrived model. And the answer is that, well, at least in computer science, theoretical computer science, there's a good reason for proving at least lower bounds in this model, or upper bounds, as we shall see. It's related to lower bounds on specific problems in this model can lead to lower bounds on threshold circuits or neural nets, I guess, can lead to faster algorithms for 3-sat. Sounds very surprising connection, but upper bounds will yield that. Has implications to data structure lower bounds. I'll not elaborate. These connections are highly non-trivial, but just to rest assured that this model is important, and we'll encounter a very similar model in the index coding problem, which I hope I'll get to. So, but the model clear, so it's a very simple definition. So we define the communication. So one observation is that unlike the number in hand, so to speak, model, where each player sees only his own input, here the communication cost of any problem is upper bounded by the number of basically the number of bits required to, the input of a single player, because the Klim can always tell me what is the input on my forehead, and then I know everything, right? Okay, so the intuition is that this is a really strong model, so it should be hard to prove lower bounds on, but so it's a very strong model because of the overlaps between different inputs. And arguably the most important problem, in communication complexity in general, but in this field in particular, is the number on forehead set disjointness problem, in which I guess all of you can figure out the problem. So it's just each player receives a subset. The input of each player is a subset out of n possible elements, and the goal is to determine whether there's a common element that that appears in all the sets, right? So again, the trivial upper bound on this problem is n, as always. Very surprisingly, there's a much better protocol. You can solve this problem, I think, with zero error using k times n over 2 to the k bits. And really, if you want to read, if you want to see why communication complexity can do non-trivial things, read this paper. It's a 2 or 3 page paper. And in my opinion, it's one of the jewels of communication complexity. It's a beautiful, highly non-trivial protocol. So it's very nice. How about lower bounds? So the best lower bound we know of is captures basically the right dependence on k. But so first of all, so it happens. So I just want to notice that this result implies that if we have logarithmically many players, the problem becomes really easy. We can solve this problem in roughly log n communication. Sorry?
In your model, there is no randomness.
No, what do you mean there is no randomness? No, I want to talk about in fact, if there's no randomness, then Anoop and Amir last year showed that for deterministic protocols, you actually do get the full, basically n over 4 to the k or something lower bound.
This was deterministic.
This protocol is deterministic. It's so zero error. Nevertheless, it achieves this. And Anoop and Amir last year proved that this is the best you can do essentially if your protocol is deterministic. But still, what we really care about is randomized lower bound. So if the players have or have a, can err with probability of a third, then the best lower bound we know of is only root n over 2 to the number of players. And this has been open for, it's been improved by Scherstoff from n to the fourth or something. But this is essentially the state of the art. And I want to mention that really this problem is not just, it's not just a sport. It's really an important problem. So if I'm not mistaken, if it turns out that this problem does admit a root n protocol for, let's say, for 3 players, so k is basically negligible here, then you can solve 3-sat in sub-exponential time, which would probably knock most of the people here off their chairs. On the other hand, if you prove a linear lower bound, I believe you get new circuit lower bounds. Is that true? Or is that? Oh, so maybe that's.
To get circuit, the consequences of other cases, you need to find a function where you get a lower bound of like n that works for k that's even bigger than y, which is not possible for the channel.
Oh, really? So I thought that even 3-party set disjoints. Okay, so I take it back. Sorry.
You need to find some other function for which you can prove the lower bound, which works even for k that's bigger than y.
Oh, I see. So this is not, it's not possible for disjoints because of this protocol. I see. Yeah, so I guess Anoop will hopefully. Yes. So I should say you should talk to Arkadev and Anoop about this model mostly. So what I wanted to say in the maybe last 10 minutes is, okay, so I didn't mention information theory so far. And indeed, this lower bound was proven by techniques which are very different than information theory. It's like polynomials and approximate degree notions, and basically algebraic techniques. Very much unlike the 2-party setting of disjointness, where the cleanest proofs we have are information theoretic, using information complexity. However, there's an intermediate problem that seems possible to pin down using information theoretic techniques, and this is why I wanted to talk about it, which is still, so K, we're only focusing on 3 parties, but the model of communication is much weaker. We only allow 1 round of communication. In fact, it's not just 1 round, it's a simultaneous model. So in this model, Alice, Bob, and Charlie are playing. Charlie's input is Z, it's on his forehead, so he sees only X and Y, and so forth. But the model of communication is restricted, so Alice and Bob are allowed to send simultaneously 2 messages to Charlie, who is then required to declare whether the inputs are disjoint or not. And that's it. So once they're not allowed to communicate, they can correlate their strategy in some weird way, but they're allowed to send the message, and then the protocol is over. Charlie has to declare and he has to be correct with probability 2/3 or so. Is that clear? Okay, so what is the best lower bound we know in this model? Still only root n, which is not better than what we know for the general model. However, the proof for this root n is easier than the Scherstoff root n proof for arbitrary protocols. I won't sketch it, but still, it seems like, at least in my opinion, and a few others, it seems like beating this root n, even for this simultaneous model, will be a nice step towards the general problem. So the only thing I want to say, I want to propose the candidate hard distribution, which it's going to be a very easy distribution if you allow even 2 rounds. But for this simultaneous model, it's going to be a hard distribution that we believe requires linear, basically, communication. So what is the hard distribution? So I need to give you a distribution on x, y, and z, right? So x and y will be n-bit strings, which they're just uniform random subsets of n elements of size, let's say, n over 10 or so, conditioned on having a unique intersection. Okay? So they intersect only in one place. Let's call it J. So it's a coordinate J. Okay? And what is Charlie's input? Charlie's input is just a uniform n-bit string Z. All right, so what I claim is that it's easy to see that the inputs, what determines the disjointness of the players, because x and y intersect only in one place, the jth bit of z sub j, right, completely determines whether the inputs are disjoint or not. In other words, Charlie has to decode the bit zj with probability 2/3 in order to determine whether the inputs are disjoint or not. Make sense? Okay, so from this point on, this is just into a one-line intuition. So what makes us think that this problem, so obviously, so there's a very trivial two-round protocol for this, just to make, so, you know, Charlie sees the intersecting index, he'll just tell the players, and then in the second round, everything will be over. Okay, but remember, our model does not allow Charlie to speak. Alice and Bob send simultaneous messages, and for this model, we believe the problem is hard. And I'll just give a 2-minute intuition. So I guess the intuition is clear, right? So, you know, Alice sends a message M1, right? But she doesn't know the index J, right? J on her side is, essentially she has zero information about, well, she has n over 10 elements, so she knows it's one of these 10 elements, but she has no further information. So she basically doesn't know anything about J, right? So it sounds plausible that, you know, in order to say something about J, she has to send, you know, all of her message, a linear. It would make sense that the information that her message conveys to Charlie with, what I want to say that Alice will, So it makes sense to assume that the information that Alice sending M1 will convey to Charlie with input xy scales as something like the size of M over n, because J is uniform on a subset of roughly n elements, which would, of course, prove that M has to be linear and so forth. But of course, this is in no way, this is just a vague intuition. Okay, and so Alice and Bob, remember the slide from the beginning of this talk. So this is exactly the scenario which we don't understand, and it sounds it sounds like a simple argument, but who knows, right? So marginally, Alice and Bob know nothing about J. They cannot collaborate, they cannot communicate with each other, but still somehow they can devise a strategy. And there are such examples in other problems where even without communicating, they can correlate their answers in a way that the information that Bob's message conveys on the index on ZJ, which is what Charlie is interested in, conditioned when you condition on M1. If you don't condition, it will be very small. But if you condition on N1, then we have no way to, I don't know of any way of bounding this term.
So you mean that the pair M1, M2 can have information?
Yeah, Charlie receives M1 and M2. M1 and M2 are simultaneous messages, so the players cannot communicate, but nevertheless they can do something like polynomial interpolation, which we've saw in, if you guys know the private information retrieval problem, you can do really nasty things even without communicating. This seems like really a real barrier that at least, so we don't know. Maybe I should say it reflects mainly my opinion and experience, miserable experience, and that of a few others. I'm not sure. Maybe, the hope is that other people have other tools or techniques. But for this model, I'm not. Probably not, right? I think it was, Yeah. So that's the second problem.
In the information theory language, there is a problem called correlated map, which captures your.
What's the name of the
It's
problem?
called a correlated map. That's kind of captures exactly. There's an open problem for 40 years. So what you're stating in some sense is a well-known hard problem in information theory. Because of this presence, the difficulty is the though they're not allowed to communicate, they have correlated messages. They want to communicate simultaneously. That's a well-known hard problem. So I don't know what
I see. Yeah.
we can say off the top.
Mm-hmm.
And there this person was construct both messages, but they have some correlated.
I see.
So this is considered a hard problem.
Okay. I'll try to to.
That's the key word to Google.
I see.
Multiplex channel. It's a multiple access channel because
I see.
Mac. Yes. So that's the Google one.
Okay, so I probably have 5 minutes or so. Okay. So let me just talk about index coding. I assume that this is a topic that information theory people know probably much better than I do. So in some sense, the index coding problem is it's almost a special case of the number on forehead model with zero communication, except there's some, I would say, a non-deterministic version of number on forehead. So in the index coding problem, a sender, so you can kind of see the recurring theme in this talk. A sender wants to encode n uniform bits in a way that each user of the n, so user I needs to decode the bit xi. But the twist is that each user has some side information, which could be an arbitrary subset of the bits, excluding, of course, the ith bit. So it's again, the ith bit is on his forehead, and he sees some other side information. So of course, so if the sender was allowed to communicate with each player, privately, this is basically a Slepian-Wolf type problem, right? But the twist is that here it's a broadcast channel, so he has to send a single message to everyone, which is viewable to everyone, and condition of this message, each player has to correctly decode his own bit, right? And this is what makes the problem hard. And of course, the question is, what is the cheapest message? What is the shortest message, or what is the least amount of entropy that is required to perform this task? So is the problem clear? You can view this as a number on forehead instance with zero communication, where there's some magician. It's like kind of a non-deterministic version of number on forehead. So let's take a look at maybe the easiest case. Suppose that each, and this is almost on the level of an exercise, but it makes you understand why you can do non-trivial things here. So suppose that each player gets his, that xi or iid as usual, and each player sees all the rest of the bits. So like in the standard number on forehead model. So each player gets a hat, it's red or blue, and he sees all the rest of the hats, and each player needs to correctly guess his own hat. And the question is, what is the cheapest, what is the cheapest message the sender can send them? How long will it be? Right, so he'll just send right. So it's clear that each player, no player can guess his own hat with probability better than half because it's independent of the rest of the hats. However, the players, even though they're not allowed to communicate, they can correlate their answer. They can just guess that the parity of all the bits is 0, right? So this is a deterministic strategy. They will be correct with probability half, and conditioned on being correct, everyone will decode their own hat correctly because they know the parity and they know the rest, so they can decode their own hat, right? So this is quite surprising, given that if each player were to guess independently, they would succeed with probability 2 to the minus n, right? But here it turns out they can simultaneously guess together. That's another way of saying it, with probability half. So it's you can do non-trivial things. But of course, the more interesting, yeah.
Do they need to exchange their random bit?
Without loss of generality, we can assume that the guessing strategy is, okay, so I like to look at the dual view of what is the probability of guessing correctly, but the real problem is actually what's the length of the cheapest message that, conditioned on this message, everyone can guess correctly, and you can assume this message is deterministic, I guess. So
Why does that
somebody just sends a parity.
Sorry, I didn't.
Somebody just sends a parity of all the.
Yeah, but nobody needs to send that. Everybody can guess without getting any extra information. The computer have the guess correctly. I think you were suggesting that somebody sent the bits. That's an index coding problem. But without anybody sending them any information, you can just guess that they agree on a strategy that the parity is even, for example.
So, yeah, but that's what I don't understand. If they want to agree on the parity being even, they need to exchange.
No, they want to maximize the probability that all of them guess correctly.
Right, but how do they choose that it's even?
Oh, they just guess. They just guess that the parity is 0. They guess it. With probability half, they'll be correct. Otherwise, all bets are off. So, yeah.
So the day before this takes place, they might have agreed to guess that the parity is even, for example.
But this strikes me as cheating. So they essentially communicate the bit the day before.
It's not. They don't communicate. They just correlate. The point is that even though the inputs are independent in some sense, I mean there are overlaps. The answers are not independent. The probability that I win, conditioned that you win, is in fact is either 0 or 1. So I guess, yeah, or 0 or 1.
Maybe they agree on the protocol before the numbers are written.
Yeah.
So the random bit is generated before the.
Yeah. The strategy is just a function. Think of it as just a function. It's a function that is pre-agreed on a day before. This function just tells each player, given the message, or depends how you look at it. If there is no Merlin, then each player just has a function that outputs 0 or 1, which is his guess, which is just a function of his own inputs. So in this case. Okay, so but of course the interesting question, the more interesting question is what happens for arbitrary graph structures. Suppose each player sees just a subset, a strict subset of the players. What happens then? And I won't elaborate. I don't have time to elaborate. But answering this question, at least I'm not aware of the information theory application, but at least in theoretical computer science, answering this problem or proving that the index code required for like worst case scenarios of subsets can prove a superlinear circuit lower bounds. In particular, if you heard about Valiant's shift problem, that was his basically his approach for proving that. I can elaborate on this offline. I just want to convince you that there's good motivation for this question. And I think, okay, so I don't have time really to talk about it, but okay, so how do I have like 3 minutes? 3 minutes. Okay, so what's nice about the parity strategy is that it's a linear decoding scheme, right? So each player just decodes his own hat, using some XOR operation, a linear operation, given the shares, the information that is published. And in general, it was conjectured by, I guess, Bar Yosef et al. That introduced the problem that linear strategies are in fact optimal for any index coding problem. It's probably quite a bold conjecture, but still, linear schemes are as far as I know, are known to achieve the best. There's no separation known. So, right.
It's not quite true. I mean, there's examples
I see.
where you do perform better than non-linear guessing strategies.
I see.
There
So.
it depends a bit on how. Yes, there are examples.
Oh, really? Okay. So I.
But if you
Yeah.
talk about that.
Oh. Okay. Oh, that's okay. So this. Yeah, I'm. Okay. So I take it back. What I wanted to note is that if we restrict ourselves only to linear strategies, so only strategies in which the decoding is an XOR, basically a linear function of the player's inputs, whatever the subset of bits he sees, and the information that Merlin, the sender, publishes, then it turns out that the optimal guessing strategy or the optimal index coding length is equal precisely to some graph operator, which is called the min rank of a graph. So what is the min rank of a graph? So we can always view view the graph of of the inputs of each player, which subsets each player sees, as we can encode it as a matrix, which corresponds to its adjacency matrix, right? And the min rank of this matrix, the adjacency matrix of the input graph, we are going to look at the minimum rank of a submatrix of this matrix. When I say submatrix, I don't mean I mean you can take this matrix and you can switch ones to zeros. So basically, you can choose any subgraph contained in this graph, and then you take the minimum over all possible subgraphs of the rank of this subgraph, but I force you to put ones on the diagonal. So otherwise, if you didn't have the diagonal constraint, you can just take the empty subgraph. The rank will be 0, right? 0, 1, right? But I force you to have the diagonal, and this forces some. Why is that? Intuitively, having ones on the diagonal corresponds to the constraint that each player needs to decode his own hat. I won't elaborate on this. Probably we'll hear about this more soon. I just want to end by saying that, so this quantity, I don't know if there's a lot known about it. In a natural place to start with, and there's a good motivation, is what is the min rank of GNP? So suppose we have, suppose our input graph is just GN half. Each player sees a random half fraction of all players' inputs. And the best lower bound for this, the min rank of GN half, the best lower bound is root n. Okay, this was a result by Chaviv and Landberg, I think a few months ago. I claim that there's a fairly easy upper bound of n log n, so over log n. Why is that? Well, a GN half or a random graph will have a clique of size log n or 2 log n, in fact. In fact, you can find lots of cliques of this size, so you can essentially cover GN half using cliques of size log n. Okay? And then for each clique, you only need to guess the parity, right? You basically repeat the previous strategy. Make sense? That was a little quick. So I think with Oded Regev and a student of his, Sasha Golvanev, I think we have a lower bound of n over log squared n, which almost matches this bound for, and this should be true for any constant p, even for GNP in general. But so this is kind of a first step, but I guess that's all I know about the problem. I assume we'll hear more about this next week.
Well, I mean, for lots of the different types of graphs, it's some interesting results involving the Hickman graph, bounds.
I see. So what type of bounds, like n to the epsilon?
Bounds, for example, the Hickman graph is a graph with 100 nodes and 100 edges. And then for that specific graph, you imagine you place that kind of hat game in the graph. And everybody has to guess their own hat. You can only see the neighbors.
So what is like the typical degree in those graphs?
It turns out that they can do much better than you would expect, because there was at some stage a conjecture that you could sort of. It turns out that essentially something called the guessing number is related to how many bits you
Right.
need to send to everybody. And it's about only, I think, 21 bits you need to send to everybody.
I see.
So the rest they can just recover from local information. So it is much better than you expect. Sort of.
I see.
That's a nice.
I see. So that's a nonlinear type strategy.
One is linear.
Oh, it is. Oh,
It's not known if you can do slightly better by nonlinear method, but it can be proved that it's only tiny better you can do by nonlinear method.
I see. In any case, I think this is a combinatorial measure which is interesting on its own right, so I just want to put it out there. No, it's just from the past 2 weeks. So, but it's still, being written up. So, this is kind of. So it's with Oded Regev and a student of his, Sasha Golvanev. But it's still in very early stage. We're hoping to leverage this to get. It's actually, I can say something about it offline, but it's like very fresh, so we're still. That's it. Thanks a lot.